Hi guys, let's dive in to our next section, 2.5. 2.5 is another game changer. So it almost feels like every section early on here is a game changer. So, learning limits, like this brand new idea. Then we learn about continuity. Okay, so we go a step further with limits and discuss that. Then in our previous section, 2.4, finally we defined the derivative, and we were able to find derivatives of functions at certain x values, at particular x values. And then we even took it a step further, and the climax of the course so far, let me just show you, this is from our notes in 2.4, is this right here. The derivative of f of x in terms of any x. So you tell us the function f of x. Then if we look at the difference quotient of that function and we simplify that and we perform a limit as h approaches 0, then that will give us a new function that we call the derivative, or we might say f prime of x. Okay, and we were able to do that, on an example we did with 16x squared. So, of course, that was in the previous section. Okay, so what are we going to do now? We recognize that the derivative is so big and so important. We've been making these huge strides forward, and we're about to make a bunch more. So, when calculus was being developed, this would have obviously taken many years to work through, possibly even decades for some of this stuff. But we see it in just a couple weeks, obviously. So, what is 2.5? It's basic differentiation rules. In other words, shortcuts to avoid limits. So derivatives are going to be such a huge idea that we don't even want to have to rely on this formula with the limit as h approaches 0 of the difference quotient. Even that is going to be too slow. Now that's where the derivative comes from. That's its basis. That's how it's defined. But we want shortcuts. Okay, so for particular functions, there are even faster ways to get our f prime of x function. And we're going to spend quite a few sections in this section, and then into chapter 3, we learn a bunch of these shortcut rules. They're like patterns. Okay, so I've kind of set you up well. So what is this all about? Um, ah, even more background before we get to it. We're going to be using more notations for the derivative starting in this section. Okay, so these are things that we'll get very familiar with over the next several sections because we're going to be using these a ton. So there are different notations for the derivative. Again, it's such a huge idea that different people use different notations, and lots of different notations stuck through history. So here are the four most popular and the four that we might see in this class. They all mean the same thing. So we're familiar with f prime of x. Okay, but sometimes maybe you want to refer to your function as a y equals instead of f of x, and so in that case you might call its derivative y prime. Kind of similar, right? Here's another one. This one's kind of bizarre. This means the same thing. It's still the derivative function dy over dx. Now, when you look at that, right, it looks like a fraction. It's not a fraction, but it represents the same thing as y prime or the same thing as f prime of x, dy over dx. And we can think of the little d as representing derivative, and that's a strange one. Okay, now maybe even more strange, this last one. Okay, what if we don't want to write f of x or y? What if we want to put the function itself, like the expression or the equation, what the function is, like is it 3x squared or something? Then we could use this. We could write d over dx, and then in brackets we write in what that expression is. Okay, and so Again, think of the d as standing for derivative. So this would mean I would like to take the derivative of this, whatever we see inside. Okay, so we're going to see all four of these notations here in this section. And each one of those you see there at the bottom. The derivative of f of x, or you might say the derivative of y with respect to x. All those representing the same thing. Now this with respect to x seems kind of unnecessary. Well, sure, the variable is x. Why do we need to state that? Well, later on, even in this course, we're going to see more complicated situations, and this last part at the end is going to be necessary. We need to say what it is with respect to. Okay, so just kind of take that for now. All right, let's go for it. We're going to look at a couple different types of functions and how their derivatives work out. We're going to ease into this real slow. Our first rule, shortcut rule, is this, the constant rule. And I'm just going to show you the whole thing right here. So we're thinking the simplest function you can imagine, where it's just equal to a number. So let's say f of x equals c, where c is some constant. It turns out, no matter what that number is, f prime of x will always equal 0. In other words, the derivative of a constant is always 0. And now you might think, okay, well, that sounds fine, but why is that true? Okay, imagine the graph of f of x equals c. So for any number, hey, if your function is equal to a number, that graph would be a horizontal line, right? You could think of this as y equals c, right? It's just that horizontal line happening there, crosses through the y-axis there at c. Now imagine you lay a tangent line on top of that function. So what would a tangent line look like? Well, if this is the line, say I wanted to know the tangent line maybe right there, at that location. Well, the tangent line would be laying directly on top of the original line. All right, and you may remember the derivative represents the slope of the tangent line. Well, hey, what's the slope of the tangent line right there? Well, if it's horizontal, the slope is 0. So if I've, right, so no matter where I choose my point, if I think of the tangent line, then it's always the same as the original line, and that would have a slope of 0. Okay, that's kind of a good visual justification of this rule, thinking of the derivative as the slope of the tangent line. Makes sense? Okay, very nice. Let's get a little bit more complex. This is going to be, we got a quick example here. I keep getting ahead of myself because really exciting things are happening. For example, let's say y equals 5. Well, let's take the derivative and let's use some of our new notation, right? We might say y prime as the derivative of y. And here, well, if y equals 5, then y prime equals 0, because the derivative of a constant is always 0. There you are. Okay, moving on. We're going to practice that constant rule more as the chapter develops. For now, we're going to move on to the power rule. So by the power rule, we're thinking, let's think about x raised to a power. So f of x equals x to the n. Now there's a pretty cool pattern here. It turns out, and I will explain why this is true in a moment. It turns out here, if f of x is x raised to some power, then f prime of x equals that power times x raised to 1 less than the power. So x to the n has a derivative nx to the n minus 1. And what happens is, whatever that number is, think of that number as now like shifting down, and then we've got x, and we just knock one off. We subtract one from the original exponent. Okay, I will explain. We'll see why that's true in just a second. Let's take a look at a quick example. Here's going to be the explanation. Let's ignore that just for the moment. Okay, let's take a look at this example here. Pick a simple one. How about f of x equals x to the third? So what would this pattern say about f prime of x? I'll say, well, that's the n, right? So it's like the 3 jumps down in front, x, and now it's raised to the second because we subtract 1 from 3. So f prime of x is 3x squared. And it's just that simple. Okay. I don't have a picture for you here. We're going to go back to the limit as h approaches 0 of the difference quotient. And that's how we're going to make sense of this example here. We're just going to do it for x to the third. Okay, so remember this formula, our original formula for how to find f prime of x. It's the limit as h approaches 0, f of x plus h minus f of x all over h. Okay, now let's think of f of x as being x to the third. And we'll see how this plays out. And we'll arrive at our answer here eventually. Okay, so f prime of x. Well, if we think of f of x as x to the third, then it'd be limit as h approaches 0. F of x plus h would be x plus h to the third minus f of x. Well, that's x to the third again. And it's all over h. And then we think, okay, we need to simplify this. And I've just gone ahead and done this hard work already. So f prime of x equals, I could certainly show more steps here, but I just kind of wanted to get to the point, right, and avoid, algebra that is necessary in a problem, but, you guys can double check this if you want. So if you were to multiply out x plus h to the third, right, multiply it by itself 3 times, you would get x to the third plus 3x squared h plus 3xh squared. Sorry, these exponents are a bit tiny on the screen. Plus h to the third. And then you would have your minus x to the third on the end. Okay, so just multiplying this out. Now we want to simplify. And what do you know? X to the thirds cancel. And from what's left, we can factor out an h. So I've got that here. So I take the h out, and then what's left, and I know this is very tiny, but 3x squared plus 3xh plus h squared. And then what do you know? These h's cancel. And we will plug in the 0 for the remaining h's. And when we do that, what are we left with? Well, I've got the 3x squared there, and if a 0 goes here and here, these two are gone, and all we're left with is 3x squared. Very cool. And we confirmed, yep, it does fit that pattern. Now, I really just did this for one example. It's far from a proof of the power rule that you see here, but hopefully that's convincing for you. The power rule is true. I'm not making it up. And if you want more explanation on the power rule and why it is true, then I can certainly give that to you, maybe in office hours or something like that, if you'd like more justification. But for now, let's go ahead and move on. Let's use the power rule in a lot of different examples. This is going to be so big. We're probably going to think about the power rule every lecture, every section for the rest of this class. We're going to think about this. And likely, most, if not every section, we're going to be thinking about this too, that the derivative of a constant is 0. These are so big. So let's get some practice in. In fact, a lot of your homework on this section is just going to be practicing these rules that we're learning. And we're going to be doing that for, several sections here Not every section in the near future, but a lot of them. We're going to be learning more and more of these patterns. Okay, let's take a look at this function here, y equals x to the 50th. Well, what would our derivative be if we follow the power rule? You say, well, now you notice I'm using this notation. The derivative of y is dy over dx. Okay, means the same thing as y prime, the derivative of y with respect to x. What is it here? Okay, so we move the 50 down in front, and it becomes x raised to the 49. Drop the power by 1. Done. Simple. One line. Over. Now, this is really exciting. It might not seem like all that big of a deal to you, but this is really exciting, right? Imagine trying to approach this derivative with this formula, right? That would be awful, right? X plus h to the 50th minus x to the 50th. You have to multiply this out 50 times. That'd be insane. But if you did, and if you simplified and you factored out an h and canceled, you would get this right here. Luckily, we have that pattern instead. Okay, let's try another one. And we'll practice more notation too. Ooh, how about this? Y equals x to the negative 2. This works for negative exponents as well. Let's see. Y prime. This would be a lot more fun if we were in class together and I say, what is it? Y prime. Okay, so the negative 2 comes down. X, and be careful here, subtract 1. Negative 2 minus 1 is negative 3. Negative 2, x to the negative 3. Okay, just kind of side note, a lot of times maybe in previous math courses when you saw a negative exponent, you never wanted to leave that in your final answer. That's not so much the case when you're doing calculus. We don't mind negative exponents in calculus because of the power rule. Okay, let's try another one. Oh man, it's getting better and better. A fractional exponent. F of x equals x raised to the 4/3. Same rule. What's it gonna be? You know, maybe write it out before I show it to you. Here it comes. F prime of x equals, all right, the 4/3 comes down in front. 4/3, x. Subtract 1. 4/3 minus 1 is 1/3. 4/3 x to the 1/3. Boom. Now, I definitely don't want to do that using that difference quotient limit style. No, thank you. Power rule makes life a lot easier here. Okay, moving on. Let's try another one. I got a ton of these. Okay, this is a good one. Let me cover this up just for the moment. Let's say you've got f of x equals square root x. You're like, square root x? Well, wait a second. The power rule only works when you have x raised to a power. How am I going to do square root x? Don't forget, square root x means the same thing as x to the 1/2. We can rewrite it. Okay, so if you get square root x, you got to remember, oh yeah, I'm going to think of that as x to the 1/2. Okay, so what would the derivative be now? F prime of x. All right, well, kind of similar to the last one, right? 1/2 comes down. X raised, subtract 1. 1/2 minus 1 is negative 1/2. 1/2 x to the negative 1/2. Very nice, very nice. They're still going. Let's see a different notation. Let me cover the answer up here because now this notation we haven't used yet, the d over dx with the big brackets. Let's try that. Let's try something really simple. Oftentimes, the simplest cases actually can be the most confusing ones. So let's look at a very simple case of x squared. We're going to see that a ton. So this notation means take the derivative of x squared. And so it's just going to be equal to whatever the derivative is, right? Take the derivative of this. All right, the derivative of this equals what? Let's see, x squared. Well, the 2 will come down in front, and the 2 on top will drop to a 1. Now, really, we don't need that 1. We could just say that this is 2x, right? You don't need 2x to the first. Okay, very nice, very nice. Here's another one. Again, something very simple. Even simpler, but maybe so simple it could be confusing. Let's take a look at the derivative with respect to x of x to the first. D over dx bracket x to the first, like just x. What's the derivative of just x? Same rule, right? If it's x to the first, the 1 comes down. What would the new exponent be? 0. Oh man, weird. Okay, so the 1 comes down and it becomes x raised to the 0. But hey, what is anything raised to the 0 power? And you may remember that anything raised to the 0 power is always 1. So this is like 1 times 1, and so it's 1. Now probably, if you ever see x, just remember that the derivative of x is 1. And maybe that's easier than kind of going through this middle step. You don't have to show that middle step. The derivative of x is 1. We're going to see that a lot. Okay, and I got one more for us. It's on the other side of this page at the top. I'm going to cover up the answer. Been saving this one. All right. How about this? Our last example before moving on. We got this notation, d over dx, the derivative of pi to the third. Pi to the third. Derivative of pi to the third. So you might be thinking, okay, well, it's going to take the same pattern as what we've been doing, all over. No. The derivative of pi to the third is 0. What? How is the derivative of pi to the third 0? Shouldn't we move the exponent down? This is just a number. Pi to the third is a constant. So the derivative of any constant is 0. And that was sneaky. That was very, very sneaky. Be on your toes. Be on your toes. Okay. There are some more rules coming up next. We're building up to polynomials here. Okay, that's coming up.